What I wanted to start off with is kind of just deep diving into one very specific topic that's very relevant to Ethereum and Ethereum scalability efforts, and is also highly relevant to blockchains more generally, even though it sometimes gets called under different names in different communities. And the topic is what I call stateless client witnesses. Right, so just as a recap, and I'm sure this is familiar to Ethereum people and blockchain people generally, we can model a kind of processing blocks as what we call a state transition function. So basically, the idea is that we talk about it of the state, where the state is all of the accounts, all of the account balances, all the smart contract storage, and the state in Ethereum is stored in a Merkle tree, where the root of the Merkle tree gets committed to in every block header, and every block only reads and writes to a small portion of the state, right? So for example, right now the state contains something like 1 billion objects, and an average a block might read and write to maybe up to 1,000 of the objects in the state. Stateless clients, so currently clients just hold the entire state, right? If you have what's called an Ethereum full node, then you're actually holding in your database this entire state, all of these accounts, all of these kind of contracts, contract storage, and contract code. And every time you receive a block, you're actually updating the state in the database. The way a stateless client works is, instead of the client holding the state, the client just holds the state root, right? So the client just holds this kind of 32-byte root hash that's part of the state. And the client doesn't even need to hold it explicitly, because if the client just has the block headers, and the block headers all contain state roots anyway. So if we model the original state transition functions, so the rules for processing the block and the rules for how the transactions in a block modify the state as the STF, so it's the state transition function takes a state in a block and it outputs a new state. So like, for example, if the original state said Alice has 50 coins, Bob has 50 coins, the block had a transaction that transferred 10 coins from Alice to Bob, then state prime would say Alice has 40 coins, Bob has 60 coins. We can think of a new state transition function, STF prime, where you talk about the state root instead of the state, the block, and a witness, and this outputs the new state root, which is equal to the root of the new state. So the witness basically is kind of the portions of the state that are read and modified in that particular block, along with proofs. And we can think about it as Merkle proofs, but later on we'll talk about how we can do other things too, right? So basically, in this particular case, like if the original state was Alice had 40 coins, Bob has 60, and then a bunch of other people had the original state is Alice has 50, Bob has 50, and a bunch of other people have some other coins. There's one transaction, and then the new state is Alice has 40, Bob has 60, and a bunch of people have other things. Then the state transition function, well, you would take in a Merkle root of the original state, then the block with that transaction, and then the witness would just have Merkle proofs to Alice's account and to Bob's account, and then it would output the new state root, right? So for any state transition function, if you Merkleize a state, you can kind of transform it into this new state transition function that just looks at roots, and except you have to kind of make this compromise that you add in this extra object that's called a witness. So why do we care about stateless clients, right? Like, why would you want to run a stateless client instead of running a regular full client? So first of all, stateless clients offer a lot of the benefits that full clients have. So in particular, stateless clients are fully validating. Even if there is a 51% attack, a stateless client is guaranteed to catch and reject any invalid blocks. But they have benefits. So a stateless client has a near zero initial sync time. So if you're willing to fast sync, then you would basically just download the header chain, verify the proof of work, or eventually the proof of stake on the headers, and then you would have the root, and you already have the root and you're already synced, right? So we can say goodbye to all of these 4-hour, 12-hour, whatever hour syncing processes. You just sync immediately. Clients can validate blocks out of order. This is interesting. So if a client wants to validate the entire chain's history because the client is paranoid, right now, the status quo is you have to create an archive node, which basically scans through the entire blockchain start to end, right? And that takes a long time, which is annoying. But what you can do with a stateless client is the client can potentially validate blocks even in backwards order, right? So you start with the latest blocks, and because the latest blocks are the blocks that have had kind of the least proof of work and the least social consensus around them, and so they're the blocks you need to be the most careful about. And then you start moving kind of backwards in terms of which blocks you validate. You could even trust blocks by default and only validate blocks in response to fraud proofs, or only validate blocks that have 2 children, because if a block has 2 children, then that's proxy evidence that maybe there's someone that, or sorry, blocks that have sisters, because if a block that has a sister, then that's proxy evidence that maybe someone disagrees with that block. Stateless clients do not require any disk access, so they're HDD friendly. They can work well even if you're not on SSD, even if you're not on a VPS. So VPSs are notorious for having high bandwidth, but being very bad at disk storage and disk capacity. So stateless clients are great for VPSs. Fraud-proof friendliness. So the mechanism for validating a block statelessly is exactly the same as the mechanism for validating a fraud proof. And the stateless client paradigm is in some sense mandatory for rapid reshuffling in sharding, right? So if you have a sharded blockchain where you have lots of different shards and you have only a few nodes processing the blocks on each shard, then a regular kind of stateful approach to validation is just not viable, because you cannot handle being reshuffled from one shard to another, right? If you spend 6 hours downloading the state from one shard, and then you validate some blocks, and then you get reassigned to a different shard, you have to just throw away all of that state and download a completely new state, right? Which is just not acceptable. So if, on the other hand, you have a stateless client, then there isn't this syncing process, and so you can just kind of jump around between shards, validate blocks on whatever shard you want, and you can just do it and everything will work. So those are kind of some of the benefits of stateless clients, right? And so we're interested in them in the Ethereum community as a way of getting around issues of disk space, as a way of getting around issues of needing a lot of disk access and blocks being slow to process as a result of that disk access, and because the ETH2 sharding paradigm just fundamentally requires statelessness. Now let's look at kind of concrete statistics, right? So let's kind of establish some notation. So we assume the total state size is n, and the number of objects accessed in a block is k, right? So n, you can think of it as like the total number of accounts, contracts, storage slots, everything in the state. And in Ethereum's case, it's in the hundreds of millions of kind of objects. And so we can just kind of round it off and say n is roughly 2 to the 30. So roughly a billion. And k, roughly 2 to the 10. So one way of thinking about this is that if you look at an Ethereum block that's just full of regular transactions, then you have 12 million gas divided by 21,000 per block, which will get you to somewhere around 570 simple transactions in a block. A simple transaction can access 2 accounts. One is a from, one is a to. That gets you to 1140. Then you might have some shared senders and shared recipients. And so you can get to about 1,000 objects that get modified in a block. So witness size, right? So let's assume that the state gets stored in a Merkle tree, which is how the Ethereum state is stored today. Then the number of kind of chunks, where by a chunk we mean a 32-byte hash, is roughly k times the log of n over k for the witness, and then plus another k for just the objects that you're proving themselves, right? So if you're proving, you're kind of making a multi-Merkle proof that proves 1,000 objects, then you have to obviously include the 1,000 objects themselves so that your kind of STF prime, your stateless state transition function, can actually read those objects and see what they are, plus Merkle proofs, which is basically k times the log of n over k. Now, if it's 1 object, then the length of a proof is obviously log n. If it's k objects, then why can you go a bit less than log n? Why is it k times the log n over k instead of just k times the log n? And the reason basically is that if you have lots of Merkle branches, then there's a bunch of kind of chunks at the top that are redundant, right? That there's a bunch of chunks that get shared between all the Merkle branches. Like if, for example, you just look at the second layer of the tree, well, the second layer of the tree just has 2 chunks. And so it's, you're not going to exceed 2 chunks, and no matter how many branches you have. Then the third layer, you're not going to exceed 4 chunks, no matter how many branches you have, and so forth. So in practice, if we kind of plug in numbers, right, we say, 1,000 times the log of a billion divided by 1,000 chunks, that gets us to around 20 chunks, and so around 600 bytes per access in practice. Now, I will make a bit of a side note and say that the current Ethereum tree is extremely suboptimal for this, right? The current Ethereum tree has this big problem that it's not a binary tree, it's a hexary tree, where every node has 16 children. And I mean, originally this was done for kind of database reasons, and those database reasons are kind of outdated now, basically because we've realized that we can, like, the fact that we have a binary hash structure doesn't mean that we can't use a different structure in the database layer. And so right now, Merkle witnesses are about 4 to 5 times longer than they need to be. But with stateless clients, you can knock it down to basically about 600 bytes per access in practice, and on average about 600 kilobytes for a witness of an Ethereum block. That is on average, and we'll talk about that a bit later. Now, there are also grinding attacks. So, like, for example, you can just spam the blockchain and create a whole bunch of accounts that have kind of addresses that are very close to each other. And the reason it's called grinding is because the actual position in the tree is the hash of the address, so you have to grind a bunch of numbers that hash to almost the same thing. And in the worst case, you can increase the size of a witness by up to a factor of 3, which is kind of bad. And so in the worst case, you might be looking for like some witness sizes that are in the high single-digit megabytes. ETH 1.0 currently is not very stateless client friendly, right? Well, it is in theory, but not in practice. And the reason basically is that the gas costs do not really align well with the size of a witness. So right now, 12 million gas a block, 800 gas per call if you assume 700 gas per overhead. Every call opcode can access a different account, so you can have about 15,000 calls in a block. And every call is a 3,000 byte witness to access the contract itself. So that's just the Merkle branch, plus 24,000 bytes of bytecode. And so in total, 15,000 times 24,000. And so you're looking at 400 megabyte witnesses. So one fix of this is to switch from the hexary tree to a binary tree, as we talked about. Another important fix is code Merkleization. So instead of treating the code as a single chunk, treat the code as a Merkle tree. And so you don't have to always include the entire contract. You just include the parts of the contract that got touched. And you have gas cost changes, right? So we can change the gas costs so that the gas costs actually reflect the size of a witness, make calls much more expensive, make calls even more expensive if they start reading the entire contract code, and so on and so forth. And so we think that we can get the kind of highest possible witness size down into the end of single-digit megabytes. So fixes in the pipeline, binary tree format, proposals to change the gas costs, code Merkleization, ETH 1.x, this is all happening, yay. Now, here's the challenge. Can we do better, right? Can we do better than having witness sizes that are log and over K chunks? And in particular, can we do better than requiring, in the worst case, multi-megabyte witnesses for Ethereum blocks, because there's a lot of nodes that can't handle multi-megabyte witnesses. There are 2 families of solutions to this. One of them is to just snark a Merkle proof. So basically, you replace a Merkle proof with a snark that says that there's a Merkle proof, or you can make it be a stark. If you know what a snark or a stark is, this is fairly easy to explain, and you probably understand already, right? You just replace the proof with the Merkle proof with a proof that says there is a Merkle proof, and now you've just cut out that entire K times log n over K with just like a fixed size thing, a few hundred bytes if it's a snark, and a few tens of kilobytes if it's a stark. And the second path has to do with vector or polynomial commitments. Polynomial commitments, basically, it's this special kind of hash of a polynomial. That's one way of thinking about it, except the hash of the polynomial has some extra properties. Right? And the properties basically are that if you have a polynomial p, or rather if you have, a polynomial p and you have some coordinate z, the prover can provide an opening proof, and the opening proof proves that P of Z equals A. And if the verifier has the commitment, so the hash of P, the verifier has Z and A, so the coordinate they're trying to prove and the value they're trying to prove, and the opening proof Q, the verifier can verify that P of Z equals A. So you can think of this as an alternative to a Merkle tree. So if you have a huge amount of data, you can create a polynomial where that polynomial evaluated at each coordinate is the corresponding piece of data. So P of 0 equals data chunk 0, P of 1 equals data chunk 1, P of 2 equals data chunk 2, and so forth. And you can create this fairly easily with polynomial interpolation, you know, Lagrange, FFTs, all of this math. And so we could use this to replace Merkle trees. But why do we want to do this? So to start off, kind of quickly going through the two major polynomial commitment schemes, there's KZG commitments or Kt commitments or Kate commitments, which rely on elliptic curve points. And the basic idea is you have this trusted setup where you basically you have the generator, and then you have the generator multiplied by kind of every power of the secret point. You encode a polynomial by basically kind of providing the corresponding linear combination of these points from the trusted setup. So if you are committing to x squared plus 5, you would provide the points that is g times s squared plus the generator times 5. Basically what this is giving you is this is giving you g times the polynomial evaluated at s. And then you prove P of Z equals A by doing this kind of subtract and divide trick, right? You basically provide a proof to a quotient polynomial where kind of Q of X, where Q of X equals P of X minus A in brackets divided by X minus Z in brackets. And the reason why this math works, right, is that basically if P of Z equals A, then the polynomial P evaluated at Z would equal to A. And so the polynomial P minus A evaluated at Z would equal to 0, which means that the P minus A would have X minus Z as a factor, right? That's a standard kind of theorem about polynomials, so that basically if a polynomial equals 0 at, say, x equals 5, then x minus 5 is a factor of the polynomial. And so if it divides, then you just provide kind of what the quotient is, and you can verify with pairings that the quotient actually is the quotient, right? You kind of provide this commitments to the quotient, then you multiply it by commitments to x minus z, and then you add commitments to, well, A, and you check if it equals the commitments to P. So this is one approach. The other approach is Fry, which is this kind of hash-based approach. And the hash-based approach is this kind of recursive technique that basically says, for every polynomial, we kind of split it up into two pieces, where one piece is just the even coefficients, the other piece is just the odd coefficients. And you can calculate these from P, right? So evens of x is P of x plus P of minus x over 2, and that gives you an even function. And then you have P of x plus minus P of minus x over 2, that gives you an odd function. And the thing that you notice is that evens and odds are both degree n over 2 polynomials or in x squared. So evens just has the even degree coefficients, and then odds, if you kind of divide it by x, would also have, well, it originally has the odd degree coefficients. You'll go down by 1, it just has the even degree coefficients. And so then you kind of do a random combination of them, and then you do a whole bunch of random checks to prove that kind of the thing that you committed to that is P of x actually mostly equals the thing that you committed to that is this random combination. And then you kind of reduce the problem of proving that a thing is degree n to a problem of proving that a thing is degree n over 2, and then you just repeat this over and over again. If you want to learn more about these, Dankrad from the foundation had a great article on how KT or KZG commitments work, and I wrote about how Fry works on Vitalik.ca. So these are kind of the two major schemes that we're talking about, and KT commitments are kind of the thing that gets used in schemes like Planck, and Fry is the thing that gets used in Starks. Multi-openings. So here is where we start talking about useful things, right? So why do we care about these polynomial commitments? So first of all, the witnesses are, in the case of Cat commitments, fixed size, right? So instead of being log n elements, they're 1 element, right? That's a commitments to Q. By the way, as an aside, I should say, I'm kind of abusing the terminology commitment here because these things are obviously not hiding, but you can think, if you just think about them as commitments, then it's like the goal here is not hiding information, so that's not actually a problem in practice. So multi-opening. So the idea here is that with polynomial commitments, you can prove a whole bunch of values with just one proof, with one fixed size proof. And the way that we do this is we just kind of take this equation, this kind of p of x minus a divided by x minus z equation, and we extend this, right? We basically say, we're going to create a polynomial I of x, which kind of interpolates all of the points that we want to prove, right? So if we want to prove that p of 3 equals 5 and p of 6 equals 42, then we interpolate and we create the kind of the low degree polynomial, in this case, just a straight line that equals 5 at 3 and that equals 42 at 6. And then if p actually equals 5 at 3 and actually equals 42 at 6, then p minus I would equal 0 at 3 and would equal 0 at 6. And so p minus I is going to be a multiple of z, which is kind of x minus 3 times x minus 6. And so if this thing is true, then you can provide a quotient, right? So if you provide a quotient, then kind of as before, the quotient just proves that the polynomial equals the values that you're claiming at all of these different coordinates at the same time. And so this is brilliant, right? Because now instead of having this big kind of proof where you have a whole bunch of things per item, so if we just used plain old Kate commitments, then it goes down from being log n object kind of hashes per thing you're proving down to just one elliptic curve points per thing you're proving. And now we're talking about going down even further to just one fixed size witness for everything that you want to prove. So this is amazing, right? This basically says that our witness needs to kind of go down to just the actual values plus this kind of negligible amount of data for the proof. So this seems perfect, but what's the problem? The main problem here basically has to do with kind of efficiency of generating these proofs, and in particular, efficiency of updating the state, right? So the problem is basically that the cost of kind of generating these proofs the normal way is going to be proportional to the total number of objects that you have in your state, right? So if your state contains 1 billion objects, then it's just going to take over 1 billion efforts to generate the proof. And that's big. That's unacceptable. That's way too much. Whereas with Merkle proofs, you just have a few hashes and the hashes are in the database and you kind of just read the hashes that you care about. And so, if you want to prove 1,000 objects, it's going to be O of 1,000 times log K. So with polynomial commitments, we don't really have this kind of nice property by default. And in particular, the problem gets worse because there are ways in some, using KZG commitments to pre-compute for specific or pre-compute witnesses and then recombine witnesses. But the problem is that we're not talking about a static state. We're talking about a state that gets updated with every block. And it turns out that if we don't yet know of a way that allows for kind of witnesses to be generated quickly, in a way that if it requires pre-computation, the pre-computation can be updated quickly if the state updates, because the state does update every block. So unsolved problem here, ETH research post, I'd recommend you photo this and then Google for it later if you're interested in kind of in solving this. So the challenge is basically kind of when the state gets updated, you have to update what all of the witnesses are. And Merkle trees are just really, really good at this, but commitment schemes are kind of not very good at this. So this is another kind of attempt to state the problem. I'll just, if you're interested in this, I'd recommend kind of, once again, kind of photoing this and then photoing this again. So that's one technique. Another technique is Merkle trees, right? So this kind of compromises between the Merkle tree path and the polynomial commitment path. And it basically says, we're going to have a tree of polynomial commitments, and they're going to have medium depth. So let's say depth 1024. And the witness here, now you are going to have to include kind of intermediate commitments as witnesses. So if your tree has depth 3, then you're going to actually have to include kind of what the intermediate commitments are. So that's 2 elliptic curve points, or 96 bytes per element. The update cost is minimal. And basically because like you don't actually need to pre-generate everything. And then the proof generation cost is 1024 times k field operations to prove k items. Basically, you just kind of generate everything as a polynomial. And then 1024 curve operations to actually kind of compute what your the kind of witness. And here we're once again doing one of these multi-witnesses, and it's kind of an even fancier multi-witness that walks across multiple coordinates over multiple polynomials. And the verification cost is k pairs if you do it naively, or 3 pairs if you do some extra work. Technique 3, SNARKing Merkle trees. So basically, SNARKing Merkle trees just assumes that your data structure is going to be a Merkle tree at the base. And Merkle trees are nice because, you know, if you update one item, then it's obvious you only need to update log n things, and so updates are cheap. And then if you have a Merkle proof, then you just kind of compute a snark over the Merkle proofs. So benefit, no sacrifice in witness updating cost. Benefit 2, post-quantum safe if you're using a Stark. Problem is proving time. Recent numbers from Starkware using their Stark-friendly hash function, 10,000 hashes per second, which is potentially 2 seconds to compress an Ethereum block witness, which is already just really impressive and amazing. So this already gets into the range of viability. And that, by the way, is just with a desktop computer. And then some researchers also recently made this interesting idea of using a GKR-based protocol to kind of prove hashes with kind of much fewer commitments than just field operations. So there's an ETH research post about this. So summary, stateless clients are great. Stateless clients solve lots of problems. They solve lots of problems in Ethereum. They're also potentially a path to solving problems in Bitcoin. So U3XO is the name of an effort that's doing some stateless client-like things in the Bitcoin context. But the problem is that you need to cut these witness sizes down, right? Like you can make it work with witness sizes that are 600 kilobytes average and low megabytes worst case, but it would be really, really nice to push them down further. And there's a bunch of fancy arithmetic techniques that can help us do this, right? So there's polynomial commitments, there's Merkle trees, there's snarks, and they have their different strengths and weaknesses, right? So like polynomial commitments are very mathematically elegant, but number one, we don't really know of a way of making them update friendly. And number two, there's also this problem that kind of the trusted setup size limits the number of objects that you can store, and how do we kind of get beyond that? And basically, you know, still needs more research. This is an area where we highly welcome more research, and where potentially a big opportunity to improve the scalability of both Ethereum 2.0 and other blockchains as well. So thank you.
Thank you very much, Vitalik. Let's open the floor for questions. We have Dyra Hopwood.
Oh, should I just read the questions from the chat?
I think Dyra should be able to speak now. Okay. Wait a second. Sorry?
I think unfortunately she just dropped off of the call, but she'd asked her question in the chat if you wanted to answer it there.
I mean, my understanding is that things like Halo are ultimately just a proving scheme. So like you could totally use such things to do things like start snarks of Merkle trees, but I guess I would definitely be curious to see if the kind of the math behind it can be adapted to the context of kind of making multi-proofs against the changing state. So that's definitely the sort of thing I would highly welcome us thinking more about.
Okay, thanks very much. Do we have more questions? Maybe even more generally. Yeah.
Not related to my presentation, what improvements on privacy are incoming? Okay, so in the Ethereum context, Tornado Cash, tornado.cash is the URL, exists and is a mixer and people can use it. There are other kind of efforts that kind of take the similar idea, right? So Tornado Cash basically just uses ZK snarks. So the idea is that you deposit, and then to withdraw, you make a zero knowledge proof that you sent one of the deposits without revealing each one, and they have different buckets for different denominations. So the improvements are, number one is moving beyond kind of buckets with different denominations and allowing these kind of zero knowledge transaction systems in Ethereum that allow for internal transactions and allow for kind of partial deposits and partial withdrawals. And that can kind of increase the anonymity set and the usability by a significant amount. So there's one project called ZK Opru, which is doing that. There's another project, I forget the name, I think Zero Pool, that's the name, which is doing that. Another improvement is doing the proof verification inside of an optimistic rollup instead of doing it directly, because Ethereum has lately been obviously having huge gas problems. And so if you do it inside an optimistic rollup, you can really save on the gas costs. So that's both ZK Opru and Zero Pool are doing that, I think. There's a longer term thing by Aztec, which is a ZK rollup. So that's also a kind of Zcash-like, private transaction system on Ethereum. You can send assets and potentially even do smart contract things in their language. And it uses snarks, one layer of snarks for privacy and another layer of snarks for verification. And so that cuts gas costs down on their side. So definitely a lot of kind of privacy improvements happening all around in that one. In that way, and I'm definitely excited to start using all of them.
Hi, can you hear me now?
Yes, I can.
Oh, okay. So the way of using recursive snarks is, can we go back to the slide where you stated the problem?
Sure, 1 second.
Yeah, thanks.
This one probably, or this one.
Yes, that one. Okay, so asymptotically, if you use recursive proofs, then it's reasonably straightforward to see how to do this. So the difficulty really is only the concrete cost of proving. Do you agree with that?
Wait, so what exactly would be the specific approach for how you would use recursive proofs for this?
Okay, so you start with the same thing of SNARKing Merkle trees at the leaf proofs.
Okay.
And then to just do n of those, you just have a log n depth tree of proofs.
Oh, I see. So basically, you start off by creating a snark for every kind of individual leaf, and then you would combine n of them, right? So the problem with that approach is that, like, let's say one value in the tree changes, then I think you would have to update every snark, because like every snark is
only the snarks on a path to the one that you've updated, I think.
But aren't all of them on a on that path? Because like ultimately that path changes. Like, well, so first of all, at least half the tree shares the first branch with that path, right?
There's a way around this, but we're not going to be able to go into it in just a few minutes.
I would highly welcome an ether research post from you.
Yes.
Like this could hugely benefit from us, and would love to collaborate more. And if there's a path here.
Yeah, I'm fairly confident that this is a solvable problem.
Okay. Any more questions?
I have one also a bit off topic, but related to a previous question. What's your take on front running?
Right. No, front running is definitely a challenge. And I mean, I guess the question is well, there's a few different front running questions, right? Like one question is, can we create systems that kind of avoid being front runnable entirely? And like, there clearly are some systems that can, like, you just make applications that look more like frequent batch auctions. I think the problem is that that's just like less real time and less gas efficient, and people love the real timeness of something like Uniswap, and people obviously like really care about gas efficiency. But you know, if that can be handled somehow, then, and I'm sure that would make people happy. Another approach to this is a kind of, instead of trying to solve front running, you manage it, right? And like potentially even a lot, like redirect the power to do front running to a kind of a single kind of sequencer slot that you would auction off, right? So this is the MEV auction idea that like Optimism is pursuing for their rollup, where you basically say that you have one party and you auction off the right to that slot, where that one party has the ability to kind of determine the order of transactions, and so that one part and basically kind of actually is the one that's publishing the batches for the containing kind of optimistic roll-up transactions onto the chain, and that one party would be able to kind of claim the MEV value, but you're okay with it. Or you're okay with them claiming the MEV value, and you just kind of, and then because it's an auction, you would also be kind of capturing the revenue instead of that revenue just kind of flying off and going to whoever, and you could use that revenue to like potentially fund public goods or do other things. So I would say both routes are promising. And I definitely do think that the problem is important, because that problem is like, if the status quo basically means that there's a lot of kind of dummy transactions on the Ethereum chain that are trying to participate in these gas races. And like the way Ethereum works now, if you win, your transaction gets in, if you lose, your transaction gets in. And so there's a lot of unnecessary activity that the chain needs to process. So if that can be solved, it would definitely be a huge improvement. To answer Arthur's question, wouldn't such a central entity introduce censorship issues? So there are two techniques that can be deployed to mitigate this. So one of them is that the way these optimistic rollups designs usually work is that if you're an individual user, then you can just publish your transaction on chain directly, and your transaction would just be included with some delay. So, you know, it could be 1 minute, could be 3 minutes, could be an hour. And so you can only be censored for that long. And the other approach is that if there's a badly performing sequencer, that you could imagine, you know, as a second layer of defense, some kind of delegated proof of stake type mechanism where you know, coin holders of some kind of token could just vote to kick out the central entity. And this would be a limited power, right? Because these people would not be able to vote to steal coins or kind of do anything that violates the system's basic guarantees, but it would be this kind of extra layer that ensures that the system kind of retains the property of accepting transactions in real time.